I'm going to be talking about minima and maxima. Suppose that we have a function that looks like this. A useful thing to be able to find out is when this function has local minima and maxima. That is, where it reaches its highest and lowest point in some neighborhood. For example, this point right here is a local maximum. Even though there's a point higher than it over here, there are no points higher than it within a small interval around it. In this graph, we can see two local maxima, as already pointed out, and there's also two local minima here and here. But how can we identify where these points are if we just know the equation of the function? Well, let's see what the derivative looks like at these points. For the first local maximum, the derivative, or the tangent line, is flat. This is because the point is located just between the section of the function that's going up and the part of it that's going down. So at this local maximum, the function is going straight horizontally. This means that the derivative must be 0 since the slope of the tangent line is 0. So if this point is located at x equals x0, then we can say f prime of x0 is equal to 0. Similarly, if we look at the local minimum right here, we draw a tangent line, it'll also be flat. So if this point is at x equals x1, we can also say that f prime of x1 is equal to 0. Now let's look at the remaining two minima and maxima. We have x2 and x3. If we look at the function around x2 or x3, then we can see that it's sort of pointy and isn't smooth at all. So we can't really even draw a tangent line there. In fact, the derivative does not exist. F prime of x2 and f prime of x3 do not exist. However, the function still exhibits minima and maxima at x2 and x3. So now we know that at a minimum or maximum, a local minimum or maximum, the derivative can be 0 or it can not exist. But can it be anything else? Let's consider another point in this function, say here, where the derivative exists and is not 0. If we draw a tangent line around this point, then we'll see that it either slopes up or down since the derivative is non-zero. But we know that this tangent line is a very good approximation of the function very close to this point. Let's call this point x4. So if we go just barely above x4 around here, then this point, this new point, will be higher than the point at x4. And if we go the other direction a tiny bit, then we'll see a point that's on this line, which is just lower than the point at x4. And we can do this no matter how close these points are to x4, as long as they're close enough. This means that x4 cannot be a local minimum or maximum. So in general, when we want to find the minima or maxima of a function, then we look for the points where the derivative is either 0 or does not exist. However, these points are not always going to be minima or maxima. If we consider the graph of a function that looks like this, in fact we can even say this is y is equal to x cubed, then look at the point at 0. The derivative here is going to be 0, the tangent line will be flat. However, it's clear that this is neither a local minimum or a local maximum. Only that it could be. And as we can see in this graph, it isn't. However, in general, the points where the derivative is either 0 or does not exist are called the critical points of a function. Up until now, we've only been talking about local minima and maxima, but we can also talk about global minima and maxima. That is, if we have a function like this, let's say y is equal to x squared, what are the highest and lowest points that this function reaches? So in this particular case, we can see that there's a local minimum here, which is also a global minimum. In fact, any global minimum has to be a local minimum, and the same for maxima. However, this function does not have a global maximum. As we can see, it goes off to infinity in either direction. So in general, a function can possibly not have a global minimum or a global maximum, but if it does, then it has to be a local minimum or maximum as well. A particularly interesting case is if we're trying to find the global minimum or maximum of a function that's only defined on some interval with endpoints. In this kind of case, note that it's always important to check the endpoints where the derivatives do not exist, here and here, as well as points where the derivative is 0, like here and here.